This video is audio content only. It does not contain any video footage or images. If you are expecting visual content, please be aware. This is intentionally provided in an audio-only format. We recommend listening to the audio rather than watching the screen. Thank you for your understanding. Welcome to our journey through one of Earth's most extreme chapters. Imagine our entire planet encased in ice. Oceans frozen solid, glaciers stretching from pole to pole. This wasn't science fiction. It actually happened, not once, but several times in Earth's deep past. Today, we'll explore the Snowball Earth hypothesis, how our planet transformed into a frozen wasteland, what it meant for early life, and how Earth eventually thawed. Join us as we uncover the remarkable story of when ice conquered the world and life found a way to survive against all odds. Chapter 1. Mechanisms triggering global glaciation through CO2 drawdown and ice albedo feedback. Between 720 and 635 million years ago, our planet experienced something almost unimaginable. Earth transformed from a world of oceans and continents into a frozen sphere, encased in ice from the poles to the equator. From space, our blue marble would have appeared as a brilliant white ball, glistening with frost and ice crystals. This wasn't a gradual cooling or a particularly harsh winter. This was a catastrophic climate collapse that locked the planet in a deep freeze for tens of millions of years. Understanding how Earth plunged into this frozen state requires us to examine two powerful mechanisms that worked in concert: the removal of carbon dioxide from the atmosphere and a runaway effect called ice albedo feedback. To grasp how these mechanisms could trigger such an extreme event, we need to first understand what made Earth vulnerable to this kind of climate catastrophe. The planet wasn't simply minding its business when suddenly ice appeared. Instead, a perfect storm of geological and atmospheric conditions was brewing. 700 million years ago, Earth looked very different from today. The supercontinent Rodinia, which had assembled hundreds millions of years earlier, was in the process of breaking apart. This wasn't a quick event, but rather a slow-motion tearing that played out over millions of years. As Rodinia fractured, new coastlines emerged and ocean basins widened. The breakup fundamentally changed how water moved across the planet's surface. When continents cluster together in a supercontinent, much of their interior lies far from any ocean, creating vast desert regions with little rainfall. But as Rodinia split apart, more continental area found itself near coastlines. This geographical reorganization had profound consequences. Rainfall increased dramatically across these newly accessible continental surfaces. Water that previously would have fallen over oceans now poured onto land, where it could interact with rocks through a process called chemical weathering. Chemical weathering might sound like an obscure geological process, but it plays an absolutely critical role in regulating Earth's climate. When rainwater falls on exposed rock, it doesn't just run off into rivers and streams. It interacts chemically with the minerals in the rock. Silicate rocks, which make up much of Earth's crust, undergo reactions with carbon dioxide and water. Consider the mineral wollastonite, a calcium silicate. When exposed to air containing carbon dioxide and to water, it breaks down. The calcium dissolves, silicon dioxide forms, and bicarbonate ions are created. Crucially, this reaction consumes carbon dioxide from the atmosphere. This might seem like a minor detail, but multiply this reaction across millions of square kilometers of newly exposed continental surface receiving enhanced rainfall, and it becomes a carbon dioxide vacuum. The carbon dioxide that gets locked into these chemical reactions doesn't simply disappear. The dissolved calcium and bicarbonate eventually wash into the ocean, where they can precipitate out as calcium carbonate, forming limestone on the seafloor. This transfers carbon from the atmosphere into solid rock, where it can remain locked away for millions of years. Under normal circumstances, this carbon removal process exists in balance with volcanic activity, which releases carbon dioxide back into the atmosphere. Volcanoes are Earth's way of recycling carbon that has been buried in rocks. The carbon cycle maintains a rough equilibrium, with carbon moving between the atmosphere, oceans, and rocks over geological timescales. But during the lead-up to Snowball Earth, this balance was disrupted. The distribution of continents played a surprising role in tipping the scales. During the Cryogenian period, when these glaciations occurred, continents were concentrated in tropical latitudes. This might seem counterintuitive. Wouldn't having continents near the equator, where the sun's energy is most intense, keep things warm? Actually, the opposite is true when it comes to initiating an ice age. Tropical continents are more reflective than tropical oceans. While ocean water in warm regions absorbs 88% of incoming sunlight, land surfaces reflect between 10 and 40%. This means tropical continents don't absorb solar energy as efficiently as tropical oceans would. More importantly, tropical continents experience heavy rainfall. The warm, moist air in equatorial regions rises and cools, releasing its moisture as precipitation. This creates perfect conditions for intense chemical weathering. Even as the planet began to cool, these tropical landmasses continued to receive substantial rainfall, meaning the weathering reactions that consumed carbon dioxide kept operating at high rates. Under normal circumstances, cooling temperatures would slow down the weathering process, allowing carbon dioxide to accumulate in the atmosphere and warm things back up. This negative feedback loop typically prevents runaway cooling, but with continents positioned in the tropics, weathering continued efficiently even as temperatures dropped. Now we come to the triggering events that actually pushed Earth over the edge. Evidence points to a dramatic geological occurrence, the eruption of massive volcanic provinces. Around 717 to 719 million years ago, just as the first Snowball Earth episode was beginning, enormous volcanic eruptions occurred in what is now the Canadian Arctic. This region is known as the Franklin Large Igneous Province. Large igneous provinces represent some of the most violent volcanic events in Earth's history. Unlike the cone-shaped volcanoes we're familiar with, these eruptions involve vast quantities of lava pouring out from fissures in the Earth's crust, sometimes covering areas the size of countries. These Franklin eruptions had a paradoxical effect. While volcanic activity typically warms the planet by releasing carbon, under normal circumstances, this carbon removal process exists in balance with volcanic activity, which releases carbon dioxide back into the atmosphere. Volcanoes are Earth's way of recycling carbon that has been buried in rocks. The carbon cycle maintains a rough equilibrium, with carbon moving between the atmosphere, oceans, and rocks over geological timescales. But during the lead-up to Snowball Earth, this balance was disrupted. The distribution of continents played a surprising role in tipping the scales. During the Cryogenian period, when these glaciations occurred, continents were concentrated in tropical latitudes. This might seem counterintuitive. Wouldn't having continents near the equator, where the sun's energy is most intense, keep things warm? Actually, the opposite is true when it comes to initiating an ice age. Tropical continents are more reflective than tropical oceans. While ocean water in warm regions absorbs 88% of incoming sunlight, land surfaces reflect between 10 and 40%. This means tropical continents don't absorb solar energy as efficiently as tropical oceans would. More importantly, tropical continents experience heavy rainfall. The warm, moist air in equatorial regions rises and cools, releasing its moisture as precipitation. This creates perfect conditions for intense chemical weathering. Even as the planet began to cool, these tropical landmasses continued to receive substantial rainfall, meaning the weathering reactions that consumed carbon dioxide kept operating at high rates. Under normal circumstances, cooling temperatures would slow down the weathering process, allowing carbon dioxide to accumulate in the atmosphere and warm things back up. This negative feedback loop typically prevents runaway cooling, but with continents positioned in the tropics, weathering continued efficiently even as temperatures dropped. Now we come to the triggering events that actually pushed Earth over the edge. Evidence points to a dramatic geological occurrence, the eruption of massive volcanic provinces. Around 717 to 719 million years ago, just as the first Snowball Earth episode was beginning, enormous volcanic eruptions occurred in what is now the Canadian Arctic. This region is known as the Franklin Large Igneous Province. Large igneous provinces represent some of the most violent volcanic events in Earth's history. Unlike the cone-shaped volcanoes we're familiar with, these eruptions involve vast quantities of lava pouring out from fissures in the Earth's crust, sometimes covering areas the size of countries.
These Franklin eruptions had a paradoxical effect. While volcanic activity typically warms the planet by releasing carbon dioxide, the immediate impact of these particular eruptions was to cool it. The key lies in what happens during fire fountain eruptions, where lava shoots into the air for weeks or months at a time. The intense heat creates powerful thermal upwellings in the atmosphere, like invisible columns of rising air. These upwellings can loft sulfur-containing gases high into the stratosphere, the layer of atmosphere above where weather occurs. In the stratosphere, these sulfur compounds form tiny aerosol particles that hang suspended in the air for months or even years. Sulfur aerosols are remarkably effective at reflecting incoming sunlight back into space. They act like a thin, high-altitude mirror, preventing solar energy from reaching Earth's surface. The timing of the Franklin eruptions aligns almost perfectly with the onset of the first Snowball Earth glaciation. The volcanic sulfur would have provided a sharp cooling kick just as other conditions were making the planet vulnerable to glaciation. But the Franklin eruptions had a second, longer-lasting effect. Large igneous provinces don't just produce lava flows, they create vast plateaus of fresh volcanic rock. In the case of the Franklin province, these rocks were emplaced directly in equatorial regions. Fresh volcanic rock, particularly the type called basalt, is highly susceptible to chemical weathering. Basaltic rocks contain minerals that react readily with carbon dioxide and water. When the Franklin eruption deposited huge quantities of such rock in a tropical location with high rainfall, it created ideal conditions for rapid carbon dioxide consumption. The weathering of this equatorial volcanic province would have accelerated the removal of carbon dioxide from the atmosphere. Scientists estimate that atmospheric carbon dioxide levels fell below 200 parts per million, less than half of today's concentration, which itself is elevated compared to pre-industrial levels. With less carbon dioxide to trap heat, global temperatures began to decline. This is where the second mechanism, ice albedo feedback, enters the picture. As temperatures dropped, ice and snow began to accumulate at high latitudes, in the regions near the poles. Ice and snow are incredibly reflective. Fresh snow can reflect 80% of incoming sunlight, while sea ice reflects 55 to 80%. Compare this to the ocean, which reflects only 12% of sunlight, and you can see why ice cover has such a dramatic effect. The ocean's dark surface acts like a solar panel, absorbing most of the sun's energy and converting it to heat. Ice does the opposite, bouncing that energy back into space. As polar ice expanded, it created a feedback loop. More ice meant more sunlight reflected into space, which meant lower temperatures, which allowed more ice to form. This is positive feedback, where a change in one direction reinforces itself. Climate scientists discovered that once ice advances far enough toward the equator, to within about 25 to 30 degrees of latitude, the feedback becomes unstoppable. At that point, the ice doesn't just creep forward gradually, it races toward the tropics. Picture the Earth from space during this transition. Ice sheets flow from the poles, grinding across continents and reaching coastlines. When glaciers meet the ocean, they don't simply stop. They flow out over the water, forming massive ice shelves. These shelves extend the reach of the ice, increasing Earth's albedo even further. The ice albedo feedback accelerates. Within a geological eye blink, perhaps just a few thousand years, ice reaches the equator. The sun itself contributed to Earth's vulnerability. 700 million years ago, our star was 6% fainter than it is today. This might not sound like much, but it translates to a significant reduction in the energy reaching Earth's surface. The faint young sun meant the planet required higher concentrations of greenhouse gases to maintain the same temperature. When carbon dioxide levels fell, the impact was amplified by the sun's reduced output. Another factor involved the evolution of life itself. Around this time, atmospheric oxygen was rising during what scientists called the Neoproterozoic oxygenation event. For billions of years, Earth's atmosphere had contained very little free oxygen, but photosynthetic organisms, particularly cyanobacteria, had been steadily producing oxygen as a waste product. When oxygen concentrations reached a critical threshold, it began reacting with methane in the atmosphere. Methane is a powerful greenhouse gas, roughly 30 times more effective at trapping heat than carbon dioxide over a century-long timescale. As oxygen destroyed atmospheric methane, converting it to carbon dioxide and water, Earth lost a significant source of greenhouse warming. The loss of methane, combined with falling carbon dioxide levels, created a double blow to the planet's heat retention capacity. With less greenhouse gas to trap outgoing infrared radiation, more heat escaped to space. Temperatures plummeted. The geological record suggests that global average temperatures may have fallen 12 degrees Celsius below freezing. For context, modern Earth's average temperature is about 14 degrees Celsius. A 12-degree drop below zero means the entire planet averaged colder than a typical winter day in many northern cities. What makes the ice albedo feedback particularly insidious is that it becomes self-sustaining. Unlike the carbon dioxide drawdown, which required ongoing geological processes to continue, the albedo feedback runs automatically once triggered. Ice begets more ice. The high reflectivity of the frozen surface maintains cold temperatures even if other factors change. This is why climate models show that once Earth crosses the ice albedo threshold, glaciation proceeds rapidly and completely. The timing of the Sturtian glaciation, the first major snowball Earth event, has been pinned down with remarkable precision using radiometric dating. The glaciation began around 717 million years ago and lasted until approximately 659 million years ago, a duration of 57 million years. The onset appears to have been globally synchronous. Ice didn't gradually spread from one region to another over millions of years. Instead, once conditions crossed the tipping point, the entire planet froze in relatively short order. Evidence for this synchronous onset comes from glacial deposits found on multiple continents. When geologists examine rocks from this period in places as far apart as Namibia, Oman, Australia, and China, they find glacial features dating to the same narrow window of time. The glacial deposits contain distinctive characteristics: dropstones, which are rocks that were carried by floating ice and then dropped into marine sediments; tillites, the poorly sorted jumble of rocks and clay that glaciers leave behind; and striated bedrock, showing scratches from rocks dragged along by moving ice. What makes this evidence particularly compelling is that these glacial features appear at locations that were in tropical latitudes when the rocks formed. The magnetic minerals in rocks record the orientation of Earth's magnetic field when the sediments were deposited. By measuring this paleomagnetism, geologists can determine the latitude where the rocks formed. Finding glacial deposits that formed within 10 degrees of the ancient equator provides powerful evidence that ice extended to the warmest parts of the planet. The mechanisms that triggered Snowball Earth represent an extraordinary convergence of geological and atmospheric processes. The breakup of the supercontinent Rodinia set the stage by increasing rainfall and chemical weathering. The concentration of continents in tropical latitudes ensured that weathering would continue even as temperatures fell. The eruption of the Franklin Large Igneous Province provided both an immediate cooling pulse from sulfur aerosols and a long-term carbon sink from the weathering of fresh volcanic rock. Rising oxygen levels destroyed atmospheric methane, and the faint young sun reduced the total energy available to warm the planet. Each of these factors alone might have caused significant cooling. Together, they created conditions that pushed Earth across a threshold from which there was no quick return. The ice albedo feedback took over, transforming the planet into a frozen world. This wasn't a stable equilibrium, but rather a catastrophic climate state, triggered by the complex interplay between the solid Earth, the atmosphere, and the amount of energy arriving from the sun. The mechanisms that initiate Snowball Earth demonstrate how planetary climate systems can have tipping points, beyond which small changes trigger dramatic transformations. Chapter 2: The Coldest Ocean in Earth's History. In 2024, researchers led by geologist Ross Mitchell reported the coldest ocean temperature ever measured in Earth's history, minus 15 degrees Celsius, give or take 7 degrees, during the Sturtian glaciation that lasted 57 million years. Once ice encased the planet from pole to equator, Earth became an alien world, unlike anything humans have ever witnessed. But the truly extraordinary conditions existed not on the surface, where ice up to a kilometer thick gleamed under a cold sun, but beneath that frozen shell, in the dark waters that remained liquid despite temperatures that defy our everyday understanding of when water should freeze. This finding raises an immediate question. Water freezes at 0 degrees Celsius under normal conditions. Even seawater, with its dissolved salts, typically freezes at about minus 1.8 degrees Celsius. So how could ocean water exist as a liquid at minus 15 degrees? The answer lies in salt, but not the relatively modest saltiness of modern oceans. As Mitchell put it, we're dealing with salty brines, so concentrated that calling it seawater seems inadequate. The analysis suggests that pockets of water during the Sturtian glaciation could have been up to 4 times saltier than modern oceans. To understand just how extreme these conditions were, consider Antarctica's Lake Vita, one of the coldest liquid water bodies on Earth today. Sealed beneath 13 meters of ice, Lake Vita contains water at minus 13 degrees Celsius. The water remains liquid because it's extraordinarily salty, concentrated by the same processes that operated during Snowball Earth, but on a much smaller scale. The Lake Vita brine represents our closest modern analog to the conditions that prevailed beneath the global ice cover 700 million years ago. Except the Snowball Earth brines were even colder, and they existed not in isolated lakes, but potentially throughout much of the global ocean. Discovering the temperature of ancient seawater presents a formidable challenge. We obviously can't stick a thermometer into an ocean that existed hundreds of millions of years ago. Instead, scientists have developed ingenious methods that use the chemistry of ancient rocks as a kind of geological thermometer. The breakthrough came from examining iron formations, distinctive rusty red rocks that accumulated where continental glaciers met ice-covered seas during the Cryogenian period. These iron formations are unusual. Most of Earth's iron formations are ancient, dating to a time before the atmosphere filled with oxygen, more than 2 billion years ago. The appearance of iron formations during Snowball Earth tells us something important about ocean chemistry during these glaciations.
Iron formations accumulate in water rich in dissolved iron. When oxygen encounters dissolved iron, it transforms the easily dissolved greenish ferrous form into rusty red ferric iron that precipitates out as a solid. This is why iron formations are mostly ancient relics from before atmospheric oxygenation. Once the atmosphere filled with oxygen about 2.4 billion years ago, the ocean soaked up that oxygen, and dissolved iron could no longer accumulate in large quantities. The iron would rust and settle out before it could build up to concentrations sufficient to form thick iron deposits. But during Snowball Earth, the situation changed dramatically. The oceans were sealed under ice, cut off from the oxygenated atmosphere. Without sunlight penetrating the ice, photosynthetic organisms in the upper ocean couldn't produce oxygen either. The deep ocean became anoxic, drained of oxygen, allowing dissolved iron to accumulate once again. The key to using these iron formations as a thermometer lies in isotopes. Iron comes in several different isotopic forms, with iron 56 being the most common. But lighter iron 54 also exists in nature, and it behaves slightly differently during chemical reactions. Iron 54 rusts more easily than iron 56. When iron rusts in the ocean, the remaining dissolved iron becomes enriched in the heavier isotope. If you measure the ratio of heavy to light iron isotopes in the minerals that precipitate from that water, you get a record of how much rusting has occurred. Ancient iron formations from billions of years ago, formed before Earth's atmosphere became oxygen-rich, contain isotopically very heavy iron compared to iron minerals that formed after atmospheric oxygenation. This heaviness reflects many cycles of partial rusting in an oxygen-poor environment. Each round of limited rusting preferentially removes the light isotope, gradually enriching the remaining dissolved iron in the heavy isotope. The pattern that develops tells a story about the chemical conditions when those minerals formed. Snowball Earth iron formations display particularly heavy isotopic signatures, even heavier than the ancient pre-oxygen formations. Here's where temperature enters the picture. The temperature at which iron minerals form affects the isotopic fractionation. Iron minerals that precipitate in cold water end up isotopically heavier than those forming in warm water. The temperature effect is predictable and measurable. Mitchell's team realized they could compare the isotopic composition of Snowball Earth iron formations with those from earlier in Earth's history to estimate relative temperatures. The challenge was figuring out what temperature to use as a baseline for comparison.
The researchers chose to use iron formations from the Archean eon, the period between 4 billion and 2.5 billion years ago, as their reference point. As geochemist Andy Hurd noted, it's a funny, backward situation to be in where you're using even older rocks as your baseline for understanding something that formed 700 million years ago. We don't know precisely how hot it was when those ancient iron formations accumulated, but we have reasonable estimates. The early Earth likely had a warmer climate than today, with some estimates suggesting tropical ocean temperatures around 25 degrees Celsius. Using this as a baseline, the team calculated that the waters which formed the Snowball Earth iron formations would have been about 40 degrees Celsius colder. 40 degrees below 25 gives you minus 15 degrees Celsius. This calculation involves assumptions and uncertainties. Hurd cautioned that the study is best interpreted qualitatively as strong evidence that seawater was The researchers chose to use iron formations from the Archean eon, the period between 4 billion and 2.5 billion years ago, as their reference point. As geochemist Andy Hurd noted, it's a funny, backward situation to be in where you're using even older rocks as your baseline for understanding something that formed 700 million years ago. We don't know precisely how hot it was when those ancient iron formations accumulated, but we have reasonable estimates. The early Earth likely had a warmer climate than today, with some estimates suggesting tropical ocean temperatures around 25 degrees Celsius. Using this as a baseline, the team calculated that the waters which formed the Snowball Earth iron formations would have been about 40 degrees Celsius colder. 40 degrees below 25 gives you minus 15 degrees Celsius. This calculation involves assumptions and uncertainties. Hurd cautioned that the study is best interpreted qualitatively as strong evidence that seawater was really cold, but maybe not that it was exactly minus 15 degrees Celsius. The value might be somewhat higher or lower. Regardless of the exact number, the broader conclusion stands. The oceans during Snowball Earth were extraordinarily frigid, quite possibly the coldest in Earth's entire history. Mitchell's team didn't stop with iron isotopes. They also analyzed isotopes of strontium and barium in the rocks to estimate salinity. These elements behave differently depending on the salt concentration of the water they're in, and their isotopic ratios provide clues about ancient ocean chemistry. The data from strontium and barium isotopes led to the conclusion that Snowball Earth seawater could have been up to 4 times saltier than modern oceans. Importantly, this wasn't the only line of evidence. Geochemist Jochen Brox from the Australian National University independently reached similar conclusions using a completely different method. Analyzing Snowball Earth sediments from Australia, Brox found rocks that formed in brine salty enough to reach minus 7 degrees Celsius before freezing. As Brox observed, it was very cool to get the additional confirmation it was actually very, very cold. When independent research groups using different approaches arrive at similar conclusions, it lends credibility to what might otherwise seem like an extreme and implausible scenario. But why would the oceans become so salty? The mechanism involves the same process we see operating in polar regions today, but amplified to a global scale over millions of years. When seawater freezes to form ice, the ice doesn't incorporate all the dissolved salts. Instead, most of the salt gets expelled, left behind in the liquid water. This phenomenon, called brine rejection, happens every winter in places like the Southern Ocean around Antarctica. As sea ice forms and thickens each winter, the shelf waters beneath the ice become progressively saltier. During the brief polar summer, some of that ice melts, diluting the brine somewhat, but over the course of a year, the net effect can be a gradual increase in salinity. Now, imagine this process operating not for a single winter or even a single year, but continuously for tens of millions of years across the entire planet. Ice sheets extended from the poles to the equator, persisting without interruption. The ice thickened to up to a kilometer in places. As ice formed, it continuously rejected salt into the liquid water below. That water, now denser because of its higher salt content, would sink. Meanwhile, any water that managed to freeze out from the brine would be relatively fresh, leaving the remaining liquid even more concentrated. Over millions of years, this distillation process could create pockets of extremely concentrated brine pooling beneath the ice. The brine wouldn't be uniform throughout the ocean. The ocean remained turbulent and mixed due to geothermal heating and tidal forces, creating spatial variations in temperature and salinity. Near the base of the ice, where freezing was actively occurring, the water would be coldest and saltiest. Deeper down, temperatures would increase slightly due to geothermal heating. There would also have been lateral gradients, differences between nearshore and offshore regions. Near the margins, where glaciers from continents met the sea, conditions would differ from the open ocean. The chemistry of the Snowball Ocean went beyond just cold and salty. The water was overwhelmingly anoxic, essentially devoid of dissolved oxygen. When scientists examine sedimentary rocks deposited during Snowball Earth, the chemical signatures indicate that most of the ocean lacked oxygen. This makes sense given that the ice cover blocked gas exchange with the atmosphere and prevented sunlight from reaching the water, shutting down photosynthesis. Geochemical data from iron and cerium isotopes show that while the sub-ice ocean was generally stripped of dissolved oxygen, localized oxygenated zones existed near ice grounding lines where glaciers met the seafloor. Any microorganisms that survived in the ocean would have required remarkable adaptations. They would have needed cryoprotectant molecules to prevent ice crystals from forming inside their cells, salt-tolerant enzymes that could function in hypersaline brine, and slow metabolic rates that could operate at near-freezing temperatures. Modern research on iron cycling in cold, oxygen-poor environments provides some insight into what might have been possible. Studies of ice-covered lakes that are rich in iron and low in oxygen show that microbes can still thrive under such conditions, using specialized metabolisms adapted to the extreme environment. The extreme conditions of Snowball Earth oceans weren't just of historical interest. They inform our understanding of the limits of habitability and where life might exist elsewhere in the universe. Consider the icy moons of the outer solar system, particularly Europa orbiting Jupiter and Enceladus orbiting Saturn. These moons are covered in thick ice shells, but beneath that ice lie vast subsurface oceans. Those oceans are salty, dark, and isolated beneath potentially tens of kilometers of ice, not entirely unlike the Snowball Earth ocean. By studying how Earth's ocean behaved under similar conditions, scientists can better understand what might be possible on these distant worlds.
The demonstration that liquid water can remain stable at -15 degrees Celsius when sufficiently saline expands the range of conditions under which we might expect to find liquid water, and therefore potentially life, elsewhere. It suggests that the habitable zone around other stars, traditionally defined as the region where a planet's surface temperature allows for liquid water, might be broader than previously thought. A planet that seems too cold to have liquid water might still harbor subsurface briny oceans. The Snowball Earth Ocean represents one of the most extreme environments in Earth's history, a world of darkness, bitter cold, crushing ice, and brine far saltier than any natural body of water that exists today. Yet it wasn't completely sterile. Life persisted, huddled in whatever refugia it could find, adapted to conditions that challenge our conception of habitability. The legacy of that survival is written not just in the rocks, but in the very existence of complex life today, including ourselves. The oceans that remained liquid beneath the ice, however cold and hostile, provided the lifeline that allowed Earth's biosphere to endure until the planet eventually thawed. Chapter 3. The Ice Extent Debate. When geologist Joseph Kirschvink coined the term Snowball Earth in 1992, in a short paper published within a lengthy volume concerning the biology of the Proterozoic eon, he painted a picture of a planet encased entirely in ice. The name itself conjured an image of Earth as seen from space, a brilliant white sphere, every ocean frozen solid, every landmass buried under glaciers. This hard snowball scenario suggested that the ice cover was total and complete, sealing the planet in a frozen prison for millions of years. It was a dramatic vision, one that captured the imagination of scientists and the public alike. But as often happens in science, the initial bold hypothesis sparked decades of debate, pushback, and refinement. Not everyone agreed that Earth truly became a solid ice ball. For 6 years after Kirschvink introduced the concept, the idea of a completely frozen Earth remained largely theoretical and underexplored. Then, in 1998, Paul Hoffman, a geologist at Harvard University, published work that brought the hard snowball hypothesis into the mainstream. Hoffman had spent an extraordinary amount of time in the field, accumulating 50 months of work in Namibia, where he gathered evidence of ancient glacial activity.
What made his findings particularly compelling was the pattern he observed in the rocks. Glacial deposits, the telltale signatures of ice sheets, were sandwiched between layers of limestone. This arrangement struck Hoffman as significant because limestone typically forms in the warmest parts of the ocean, where calcium carbonate can precipitate from seawater. The juxtaposition suggested that glaciers had covered areas that should have been tropical, followed by a return to warm conditions. Hoffman's interpretation was that the entire planet had frozen over during the cryogenian glaciations. The limestone beneath the glacial deposits formed in warm tropical seas. Then, ice advanced globally, covering even the equator. After the glaciation ended, limestone formation resumed. The pattern made sense if you accepted the premise of complete global ice cover. The paper describing this scenario appeared in a prominent journal and presented the hard snowball as a credible scientific hypothesis backed by geological evidence from multiple continents. But as Hoffman himself would later acknowledge, new ideas are like small children. It's best not to judge them too early because you don't know what they'll be like as adults. The hard snowball hypothesis was incomplete, and over the following years, serious problems with the scenario emerged. Biologists pointed out that complete ice cover should have caused mass extinctions, not evident in the fossil record. Geologists raised another troubling issue. The hard snowball theory predicted that with the ocean sealed under ice and temperatures far below freezing everywhere, the water cycle would effectively shut down. Evaporation from the ocean drives precipitation on land. No open water means no evaporation, which means no precipitation. The atmosphere would become extremely dry. Yet the geological evidence told a different story. Glacial deposits showed signs of active ice flow and accumulation, which requires snowfall. There were indications of an ongoing water cycle operating during the glaciation. Water was moving from the ocean to the atmosphere to the land and back again, even during the supposed deep freeze. This didn't match the predictions of a completely sealed system.
Perhaps the most perplexing problem involved the mechanism for ending a hard snowball. If Earth became completely ice-covered, how did it ever warm up again? Ice and snow are highly reflective, bouncing sunlight back into space. This high albedo would maintain cold temperatures even if other factors changed. The only plausible mechanism for breaking out of a complete freeze was a massive buildup of carbon dioxide from volcanic activity. Volcanoes would continue erupting beneath the ice, releasing carbon dioxide into the atmosphere. With no liquid water to weather rocks and remove that carbon dioxide, it would accumulate over millions of years. Eventually, the greenhouse effect from all that carbon dioxide would overpower the ice albedo feedback, and the planet would begin to warm. Calculations suggested that escaping from a hard snowball would require atmospheric carbon dioxide concentrations several hundred times higher than present levels. That's an extraordinary amount of greenhouse gas, far more than exists in Earth's atmosphere today. Yet when geochemists looked for evidence of such extreme carbon dioxide levels in the rocks, they couldn't find it. The geochemical proxies used to estimate ancient atmospheric composition didn't support carbon dioxide concentrations anywhere near that high. These problems led many scientists to question whether the hard snowball scenario was really what happened. An alternative began to take shape, one that came to be known as the slush ball hypothesis. Instead of Earth becoming entirely encased in ice, the slush ball scenario proposed that, while ice coverage was extensive and reached tropical latitudes, some areas of open water persisted, particularly near the equator. Rather than a complete whiteout from space, Earth might have looked more like a planet with massive ice caps extending toward the middle latitudes, but with a band of liquid ocean at the warmest parts of the globe. The slush ball idea addressed several of the problems with the hard snowball. If there was open water near the equator, photosynthetic organisms could have survived in those regions. Light could penetrate the water, allowing life to persist, and explaining why the fossil record doesn't show a complete collapse of marine ecosystems. Open water would also allow for evaporation and precipitation, maintaining an active water cycle consistent with the geological evidence. And if liquid water remained exposed at the surface, it could weather rocks and regulate atmospheric carbon dioxide, making it easier to understand both the descent into glaciation and the eventual recovery. The tension between these two scenarios came to a head during a workshop held in Switzerland during the summer of 2006. 65 scientists from different disciplines gathered to hash out the evidence.
geologists who studied the rocks, biologists who understood the fossil record, climate modelers who simulated ancient atmospheres, and experts in planetary chemistry all spent a week debating the nature of Snowball Earth. It was an intense meeting with passionate arguments on both sides. By the end, a consensus began to emerge, though not everyone agreed. Most participants left the workshop thinking that the oceans had never frozen completely. The evidence seemed to favor some version of the slush ball over a total hard snowball.
As one participant later recounted, the alternative to the hard snowball was a slush ball. Yes, there was a really bad ice age, but there was also lots of open ocean. This wasn't giving up on the Snowball Earth idea entirely. It was a refinement, an acknowledgement that the reality was probably more nuanced than the original dramatic vision of a completely frozen planet. But how much open water could have existed? This is where climate modeling became crucial. Computer simulations allow scientists to test different scenarios and see what conditions are physically plausible. Early models of Snowball Earth were limited by the technology available at the time. The computers that ran them simply weren't powerful enough to handle the complexity of Earth's climate system in great detail. The approximations used were necessarily crude. But as computing power increased and models became more sophisticated, scientists could simulate ancient climates with greater fidelity. Linda Sohl, a researcher at Columbia University and NASA's Goddard Institute for Space Studies, became one of the leading voices in using modern climate models to understand Snowball Earth. She and her colleagues took climate models originally developed to predict future climate change and adapted them to study the deep past. These weren't simple programs. The NASA GISS Earth System Model, known as Model E2R, is one of the most sophisticated climate simulations available, incorporating not just the lower atmosphere, but also the ocean, sea ice, land surfaces, the carbon cycle, aerosols, atmospheric composition, and even the stratosphere. Dozens of scientists from different specialties contributed to developing and refining the model over decades. To simulate Snowball Earth conditions, Sohl's team had to turn back the clock on the model. They dimmed the sun's brightness by 6% to account for how much fainter it was 700 million years ago. They rearranged the continents into the configuration they would have had during the Cryogenian, with land masses clustered near the equator, forming the supercontinent Rodinia in various stages of breakup. They adjusted atmospheric composition based on the best estimates for that time period. Then they let the model run to see what kind of climate emerged. The results were revealing. Even under extremely cold conditions, with global average temperatures dropping 12 degrees Celsius below freezing, the model didn't produce a completely frozen planet. Instead, substantial areas of open water persisted near the equator. In some simulations, roughly half of the ocean surface remained ice-free. Ice covered the poles and extended into middle and even low latitudes, but a band of liquid water stayed open in the tropics. What prevented complete freezing? Ocean circulation played a critical role. Modern Earth has powerful ocean currents that redistribute heat around the planet. The Gulf Stream, for instance, carries warm water from the tropics northward along the eastern coast of North America and across the Atlantic toward Europe. This current transports an enormous amount of heat. Without the Gulf Stream, the climate of northwestern Europe would be much colder than it is. During Snowball Earth, similar ocean currents would have existed, albeit in a different configuration because the continents were arranged differently. The climate model showed that these currents helped concentrate heat near the equator. Even though the total amount of solar energy reaching Earth was reduced, the energy that did arrive was most intense at the equator, where the sun's rays strike most directly. Ocean circulation gathered that warmth and kept equatorial waters above freezing. The ocean didn't freeze solid because it was constantly being stirred and mixed, with currents bringing warmer water from depth to replace surface water that froze or cooled. This dynamic process maintained regions of open water. Sohl emphasized that ocean circulation seemed to be key in preventing a full freeze-over. The currents acted as a brake on the runaway ice albedo feedback. Yes, ice spread extensively, and its high reflectivity cooled the planet dramatically. But the ocean's ability to transport and store heat provided a stabilizing influence that prevented the absolute worst-case scenario.
Other factors also mattered. The length of the day was shorter during the cryogenian, with a full rotation taking 21.9 hours instead of the current 24. This affected atmospheric dynamics, changing wind patterns and the distribution of heat and moisture. The team explored how this would have influenced the climate. They also considered how atmospheric carbon dioxide levels, while lower than normal, couldn't have dropped to zero. There was still some greenhouse effect operating, even if it was much weaker than today. Richard Peltier, a physicist at the University of Toronto who studies climate dynamics, pointed out another important factor that models needed to account for: topography. The altitude of land surfaces matters for glaciation. Higher elevations are colder, making it easier for ice to accumulate, even when lowlands remain ice-free. During Snowball Earth, the arrangement and height of mountain ranges would have influenced where ice could form and persist. This topographic effect could enable glaciation in some regions, even when other factors might work against it. Fully capturing these topographic influences requires high-resolution models that can represent terrain features accurately, something that continues to challenge even modern simulations. The debate between hard snowball and slushball isn't completely settled. Some scientists still argue that certain evidence supports more extensive ice coverage than the slushball models predict. There are also arguments about whether different snowball erg events might have been different in character. The Paleoproterozoic glaciation around 2.2 billion years ago might genuinely have been a hard snowball. At that time, the sun was even fainter, 16% dimmer than today, instead of just 6% dimmer. The glaciation coincided with the evolution of photosynthetic organisms that were pumping oxygen into the atmosphere, destroying methane greenhouse gases. The combination of factors might have been sufficient to freeze the planet completely. But for the cryogenian glaciations, the ones most relevant to the evolution of complex life, the weight of evidence increasingly favors something less extreme than total global ice cover. The geological evidence shows extensive glaciation reaching low latitudes. The climate models demonstrate that this is consistent with large but not complete ice coverage. The biological evidence indicates that ecosystems survived. The geochemical evidence suggests an active water cycle and carbon cycle.
What we call these glacial events matters less than understanding what actually happened. Whether we label it a hard snowball or a slush ball or something in between, the cryogenian glaciations represent among the most severe climate changes Earth has ever experienced. Ice advanced farther toward the equator than at any other time in the past 600 million years. Temperatures plummeted to levels not seen before or since. The planet spent tens of millions of years in this frozen or near-frozen state. Yet it wasn't a static, dead world. Ocean currents continued to flow. The water cycle kept operating. Life persisted, adapted, and ultimately thrived when warmth returned. The planet's climate system, even under the most extreme stress, maintained some level of dynamism and didn't collapse entirely into a frozen equilibrium from which there was no escape. Chapter 4. The Volcanic Escape. The frozen planet appeared permanently trapped. Ice stretched from pole to pole. Glaciers kilometers thick sprawled across continents and oceans alike, and the brilliant white surface reflected sunlight back into space with ruthless efficiency. The very physics that created this frozen world worked to maintain it. Ice begets more ice. Cold begets more cold. Yet Earth did escape. Not just once, but twice during the cryogenian period. The planet warmed, the ice vanished, and conditions returned to something resembling normalcy. What broke the frozen stalemate reveals one of the most dramatic climate reversals in planetary history: a slow accumulation of volcanic gases culminating in a greenhouse inferno that dwarfed anything our species has witnessed. The answer lay beneath the ice in Earth's restless interior. Volcanoes continued erupting regardless of surface conditions. Plate tectonics operates in the mantle, far below the crust, powered by heat from radioactive decay and primordial planetary formation. Molten rock wells up at mid-ocean ridges, spreading the seafloor apart. Subduction zones drag oceanic crust down into the mantle, where it melts and fuels volcanic arcs. Hotspots punch through the crust, creating chains of volcanic islands. All this activity releases gases from Earth's interior, and the most important is carbon dioxide. Normally, the carbon cycle maintains balance.
Volcanoes emit carbon dioxide, which enters the atmosphere and traps heat. Rainfall washes that carbon dioxide out of the air through reactions with rocks, eventually locking it in minerals like limestone. But Snowball Earth shattered that equilibrium. Ice smothered the continents, burying the rocks that would normally weather and consume atmospheric carbon dioxide. Glaciers covered the land surface under kilometers of ice. The few exposed rocks existed in areas so cold that chemical weathering slowed to nearly nothing. Extreme cold hampered reaction rates. Precipitation dropped to a fraction of normal levels. One of the two main carbon dioxide sinks essentially shut down. The ocean provided the other major sink, but ice sealed much of the ocean's surface, preventing gas exchange with the atmosphere. The biological pump that normally transfers carbon from surface waters to deep sediments weakened severely. Marine life persisted in whatever refugi existed, but global biological productivity fell to a shadow of normal levels. With removal mechanisms crippled, volcanic outgassing dominated. Every eruption added more carbon dioxide. The gas accumulated year after year, century after century, millennium after millennium. This wasn't rapid. Estimates suggest 10 million to several tens of millions of years for atmospheric carbon dioxide to climb from pre-glaciation levels to the concentration necessary to trigger deglaciation. How much carbon dioxide was required? Climate models suggest escaping snowball conditions demanded concentrations reaching about 100 times the present atmospheric level, roughly 10% of the atmosphere by volume. Earth's atmosphere today contains about 400 parts per million of carbon dioxide. 10% represents an extraordinarily high concentration, roughly 250 times higher than pre-industrial levels. Geochemical evidence from rocks deposited at the end of the Marinoan glaciation supports carbon dioxide levels in this range.
The timing of deglaciation provides crucial constraints. Radiometric dating using uranium, lead, and rhenium-osmium techniques pinned down when the Sturtian glaciation ended, between 659 and 658 million years ago. The Marinian glaciation ended between 636 and 635 million years ago. These terminations appear globally synchronous. Evidence from South China, Southern Australia, Namibia, and Laurentia all point to the same narrow windows. This synchronicity reveals something critical. The mechanism operated globally and relatively quickly, consistent with carbon dioxide reaching a threshold that affected the entire planet at once. Once carbon dioxide concentrations reached the deglaciation threshold, events unfolded with shocking speed compared to the millions of years required to build up greenhouse gases. The first areas to melt would have been the tropics, where incoming solar radiation remained strongest. As equatorial ice thinned and cracked, dark ocean water appeared beneath. The ice albedo feedback that had driven Earth into glaciation now reversed direction. Less ice meant more solar energy absorbed, warmer temperatures, more melting, and even less ice. The feedback loop became a deglaciation accelerator. Climate models suggest that once the tropical ocean began opening, the ice line retreated from equator toward poles in approximately 2,000 years. 2,000 years sounds lengthy from a human perspective, but it's an eye blink geologically. The planet went from ice-covered to ice-free faster than a giant sequoia takes to reach maturity. The climate emerging at Snowball Earth's end bore no resemblance to the frozen world preceding it or the temperate conditions that would eventually follow. Instead, Earth plunged into a greenhouse inferno. Atmospheric carbon dioxide levels 100 times higher than today, combined with a dark, highly absorptive ocean surface. The planet swung from the coldest conditions in its history to some of the hottest. Scientists have developed creative ways to reconstruct these extreme temperatures. One technique involves iron isotopes in ancient iron formations. The ratio of iron 56 to iron 54 varies with temperature during iron mineral precipitation. By measuring these ratios in rocks deposited during and after Snowball Earth, researchers determined that tropical ocean temperatures might have exceeded 50 degrees Celsius, hot enough to make swimming lethally dangerous. For comparison, a hot tub typically reaches 40 degrees Celsius, and water at 50 degrees causes burns with prolonged exposure. This extreme heat created a hyperactive water cycle.
The timing of deglaciation provides crucial constraints. Radiometric dating, using uranium lead and rhenium osmium techniques, pinned down when the Sturdian glaciation ended, between 659 and 658 million years ago. The Muronian glaciation ended between 636 and 635 million years ago. These terminations appear globally synchronous. Evidence from South China, Southern Australia, Namibia, and Laurentia all point to the same narrow windows. This synchronicity reveals something critical. The mechanism operated globally and relatively quickly, consistent with carbon dioxide reaching a threshold that affected the entire planet at once. Once carbon dioxide concentrations reached the deglaciation threshold, events unfolded with shocking speed compared to the millions of years required to build up greenhouse gases. The first areas to melt would have been the tropics, where incoming solar radiation remained strongest. As equatorial ice thinned and cracked, dark ocean water appeared beneath. The ice albedo feedback that had driven Earth into glaciation now reversed direction. Less ice meant more solar energy absorbed, warmer temperatures, more melting, and even less ice. The feedback loop became a deglaciation accelerator. Climate models suggest that once the tropical ocean began opening, the ice line retreated from equator toward poles in approximately 2,000 years. 2,000 years sounds lengthy from a human perspective, but it's an eye blink geologically. The planet went from ice-covered to ice-free faster than a giant sequoia takes to reach maturity. The climate emerging at Snowball Earth's end bore no resemblance to the frozen world preceding it or the temperate conditions that would eventually follow. Instead, Earth plunged into a greenhouse inferno. Atmospheric carbon dioxide levels 100 times higher than today, combined with a dark, highly absorptive ocean surface. The planet swung from the coldest conditions in its history to some of the hottest. Scientists have developed creative ways to reconstruct these extreme temperatures. One technique involves iron isotopes in ancient iron formations. The ratio of iron 56 to iron 54 varies with temperature during iron mineral precipitation. By measuring these ratios in rocks deposited during and after Snowball Earth, researchers determined that tropical ocean temperatures might have exceeded 50 degrees Celsius, hot enough to make swimming lethally dangerous. For comparison, a hot tub typically reaches 40 degrees Celsius, and water at 50 degrees causes burns with prolonged exposure. This extreme heat created a hyperactive water cycle. Warm oceans evaporated vigorously, pumping moisture into the atmosphere. That moisture rose, cooled, and fell as torrential rain. But this was not ordinary rain. With so much carbon dioxide in the atmosphere, rainwater became carbonic acid, essentially a weak acid solution falling on rocks freshly exposed by retreating glaciers. Glaciers grind rock into powder, creating vast quantities of finely pulverized material. This glacial flour, with enormous surface area, proved extremely vulnerable to chemical weathering. Acid rain attacked the debris with extraordinary intensity. Calcium-bearing minerals dissolved readily, releasing calcium ions into solution. Rivers carried calcium-rich water into the ocean in a massive pulse of alkalinity. When calcium-rich freshwater met seawater, it triggered calcium carbonate precipitation. This formed the distinctive cap carbonates that sit directly atop glacial deposits worldwide, marking the transition from icehouse to greenhouse. These limestone and dolostone layers, typically meters to tens of meters thick, appear globally. They display unusual characteristics distinguishing them from ordinary limestone. Many show peculiar sedimentary structures, sometimes interpreted as giant ripples, suggesting deposition under unusual conditions. The carbon isotope composition is also strange, with values near -5 per mil, close to the isotopic signature of mantle carbon. This could indicate limited biological processing during deposition, or it might reflect isotopically light carbon released from methane deposits that destabilized as oceans warmed. The ocean underwent dramatic chemical changes during deglaciation. Boron isotopes in rocks deposited before, during, and after the Muronian glaciation provide a record of seawater pH, showing that ocean pH dropped dramatically. The ocean became much more acidic. This makes sense given the enormous carbon dioxide dissolving into seawater. Carbon dioxide in water forms carbonic acid, lowering pH. The ocean acidification during Snowball Earth deglaciation would have been far more severe and rapid than acidification currently occurring from human emissions. Additional geochemical evidence comes from lithium isotopes. Measurements of LiThium-7 to lithium-6 ratios in postglacial rocks reveal mixing between meltwater carrying high LiThium-7 values and hypersaline seawater with low LiThium-7 values. This provides direct chemical fingerprints of the freshwater influx from melting ice mixing with dense, salty water that had concentrated beneath the ice. The lithium isotope data supports the hypothesis that oceans developed a stratified structure during glaciation, with a layer of hypersaline water beneath the ice that mixed violently with meltwater during deglaciation. Ocean circulation patterns played crucial roles in heat distribution during deglaciation. Though the details remain uncertain, ancient equivalents of modern currents like the Gulf Stream would have transported heat from tropics toward poles, accelerating ice retreat. As ice melted and freshwater flooded into oceans, these circulation patterns underwent repeated reorganization, creating pulses of warmth and periods of relative stability. As deglaciation proceeded, ocean chemistry didn't just acidify and stay that way. Eventually, as weathering removed carbon dioxide from the atmosphere and delivered alkalinity to the ocean, pH rebounded. This deacidification also appears in geochemical proxies. The ocean experienced a complete pH cycle, from acidification driven by rising atmospheric carbon dioxide during late glaciation, through extreme acidification during the greenhouse peak, to gradual deacidification as weathering removed carbon dioxide. Few other times in Earth's history show such extreme and rapid ocean chemistry changes.
The intense chemical weathering during the post-glacial greenhouse had one critical consequence. It removed carbon dioxide from the atmosphere. The same intense rainfall and rapid rock weathering that created cap carbonates also drew down atmospheric carbon dioxide levels. This weathering operated like a thermostat, albeit with lag time. Higher carbon dioxide meant warmer planet, more intense water cycle, faster weathering. Fast weathering removed carbon dioxide, lowering temperatures, eventually slowing weathering. Over roughly 10 million years, weathering and carbon burial brought atmospheric carbon dioxide from its extreme peak back toward moderate levels. Eventually, carbon dioxide fell enough that the planet could support polar ice caps again. The intense greenhouse moderated into something more temperate. But the transition wasn't simple or instantaneous. Geological evidence shows marine flooding of continental margins continued long after ice sheets disappeared. When massive ice sheets rest on continents, their weight depresses the crust, pushing it down into the mantle. This creates a peripheral bulge or forebulge around the ice sheet, where crust gets pushed upward. When ice melts, depressed areas slowly rebound and peripheral bulges collapse. This isostatic adjustment takes millions of years to complete. The collapse of these bulges, combined with thermal expansion of warming ocean water, meant substantial sea level rise. Coastlines exposed during glaciation flooded. Marine waters advanced across continental shelves, creating shallow seas. These transgressive sequences show up in the rock record as marine sediments deposited atop glacial or non-marine deposits. The flooding continued long after ice ceased being a major landscape feature, a lingering consequence of massive climate upheaval. The story of Snowball Earth deglaciation illustrates profound points about planetary climate systems. First, climate has tipping points where feedbacks suddenly reverse direction. The same ice albedo feedback that drove Earth into glaciation drove it out once conditions changed. Second, planets have natural thermostat mechanisms, but those thermostats can break under extreme conditions and require millions of years to reset. Third, climate systems have enormous inertia. It took tens of millions of years to accumulate enough carbon dioxide to escape glaciation, but once ice began retreating, the planet swung wildly in the opposite direction, into extreme heat, before eventually settling into something moderate. The deglaciation left behind a unique geological fingerprint. Cap carbonates marking the end of cryogenian glaciations are distinctive enough that geologists identify them in rocks worldwide. These limestone layers represent a global event, a planetary-scale transition recorded in stone. The synchronicity of their deposition, confirmed by radiometric dating, provides powerful evidence that Snowball Earth deglaciations were true global events, not regional phenomena happening at different times in different places. Perhaps most remarkably, Earth went through this extreme cycle twice in relatively quick succession, geologically speaking.
The Sturton glaciation lasted from 717 to 659 million years ago. Then, after a non-glacial interlude of 9 to 19 million years, the Marinoan glaciation occurred from approximately 645 to 635 million years ago. Each time, the planet froze over, carbon dioxide built up, and eventually the greenhouse effect overpowered the ice, swinging climate from one extreme to the other. The fact that Earth could endure this twice and still maintain a biosphere capable of eventually producing complex life speaks to the resilience of both the planet and life itself.
Chapter 5. After the Ice. When Earth finally thawed from its second major cryogenian glaciation around 635 million years ago, the planet was unrecognizable compared to the world that had existed before the paired glaciations began 82 million years earlier, despite the brief clement interlude between them. But the most profound changes were not geological or atmospheric, they were biological. Cells had learned to cooperate in unprecedented ways, building multicellular bodies with specialized tissues and coordinated functions. Within 50 million years of the Marinoan deglaciation, a time span that seems long to us but is remarkably brief in evolutionary terms, the oceans teemed with complex multicellular animals. Creatures with bodies, with organs, with nervous systems and muscles appeared seemingly out of nowhere. This explosion of biological innovation stands as one of the greatest mysteries in the history of life, and mounting evidence suggests that the Snowball Earth glaciations didn't just happen to precede this revolution, they may have caused it. The puzzle begins with a simple observation that baffled paleontologists for decades. For more than 3 billion years after life first appeared on Earth, it remained stubbornly simple. Bacteria dominated. Single-celled organisms with more complex internal structures, the eukaryotes, eventually evolved, but they too remained solitary cells floating in ancient seas or forming simple colonies. There were no animals, no plants as we would recognize them, no fungi building mushrooms or molds. Life was microscopic and uncomplicated. This extended stability is all the more striking when we consider that virtually no ice sheets existed during the intervening 1.5 billion years between the early Paleoproterozoic glaciations and the cryogenic events. The planet had enjoyed a long period of relative climatic stability, yet life remained simple. Then, in what seems like a geological instant after the cryogenic freeze, everything changed. Complex animals appeared, diversified, and spread across the globe. The timing of this transformation seemed too close to be mere coincidence, but the connection wasn't obvious at first. If anything, the initial expectation was that Snowball Earth should have devastated life, not promoted it. Covering the planet in ice for tens of millions of years seems like the kind of catastrophe that would drive mass extinctions. Indeed, when the hard snowball hypothesis was first proposed, biologists pointed out that completely freezing the ocean should have collapsed marine ecosystems. Photosynthetic organisms need light, and a kilometer of ice blocks sunlight effectively. Without photosynthesis, the base of the food chain disappears. Every organism that depends on those primary producers should have starved. The hard snowball predicted that the fossil record should show a massive die-off during the cryogenian, the kind of extinction that would leave obvious scars in the paleontological record. Yet when researchers examined the fossils, they found something unexpected. Yes, there were extinctions during the Snowball Earth periods, some lineages disappeared, but the extinctions were modest, not catastrophic. Life somehow persisted through conditions that seemed utterly inhospitable. This observation became one of the key arguments against the hard snowball scenario and in favor of the slushball hypothesis. If open water existed somewhere on the planet, even just in tropical regions, then refugia existed where life could survive.
Understanding where and how life survived the deep freeze requires us to consider what kinds of organisms existed before the Sturtian glaciation began. The Earth of 720 million years ago was inhabited primarily by bacteria and single-celled eukaryotes. Cyanobacteria, which perform photosynthesis and release oxygen, had been around for billions of years. More complex single-celled organisms had evolved various sophisticated structures within their cells, including nuclei that housed their genetic material and organelles that performed specialized functions. Some eukaryotes had already evolved the ability to move using whip-like flagella. Others had developed the capacity to engulf and consume other cells, becoming predators at the microscopic scale. These organisms faced an existential challenge when ice advanced across the ocean's surface. In open water regions that froze over, the upper ocean became dark. Photosynthetic organisms near the surface would have died off rapidly. But the ocean isn't uniform. Temperature gradients exist, currents flow, and even during Snowball Earth, geothermal heating and tidal forces kept the deep ocean mixed and turbulent. Life had options, if it could adapt. One refuge existed along the grounding lines where glaciers met the seafloor. Subglacial meltwater carrying dissolved oxygen would seep out into the otherwise anoxic ocean, creating pockets of habitable water. These zones would have been tiny compared to the vast ocean volume, but size doesn't matter for microorganisms. A cubic meter of oxygenated water can support billions of bacterial cells. Recent research examining rocks from Snowball Earth has found geochemical evidence for these oxygenated refugia. The isotopic signatures of iron and cerium in sediments show zones of increased oxidation near where glaciers would have rested on the seafloor. Another refuge existed in thin films of meltwater on the ice surface itself, particularly in equatorial regions where solar input remained strongest. Even under extreme cold, dust accumulating on the ice surface would lower its reflectivity, the albedo, allowing enough solar heating to create pockets of liquid water. These superglacial meltwater ecosystems, though oligotrophic and nutrient-poor, could support cyanobacteria and certain hardy eukaryotes. The conditions favored different organisms than had dominated before the freeze. While simpler cyanobacteria had thrived in the preglacial oceans, the challenging conditions of these surface refugia may have given advantages to more complex algae, eukaryotic organisms with greater cellular sophistication that could better regulate their internal chemistry. Meltwater flushing through cracks in the ice enabled organic material to be buried in sediments below, preserving a record of these tenacious survivors.
Even the hypersaline brines at depth could have harbored life. Modern research shows that specialized microorganisms can survive and even thrive in extremely salty, cold environments. The brines of Lake Vita in Antarctica support microbial communities despite temperatures of -13 degrees Celsius. Snowball Earth brines were colder still, potentially reaching -15 degrees, but that doesn't necessarily rule out life. Evolution is remarkably good at finding solutions to extreme environmental challenges. Microorganisms can produce cryoprotectant molecules that prevent ice crystal formation inside cells. They can develop salt-tolerant enzymes. They can slow their metabolism to a crawl, entering a state of near-suspended animation until conditions improve. The remarkable fact isn't that some life went extinct during Snowball Earth. The remarkable fact is that so much survived. The Sturdian glaciation lasted approximately 58 million years, followed by the brief interlude, then the Merinioan for an additional 10 to 15 million years. The continuity of the fossil record across this immense span tells us that major groups of microorganisms made it through. They were battered, their populations reduced, their distributions limited to whatever refugia existed, but they endured. And when the ice finally retreated, those survivors found themselves in a world of new opportunities. Between the Sturdian and Merinioan glaciations, Earth enjoyed a relatively brief respite. This non-glacial interlude lasted somewhere between 9 and 19 million years. The climate remained cooler than modern Earth, but liquid water was abundant, and sunlight reached the ocean surface. This was the period when something extraordinary first appears in the geological record: evidence of animals. The evidence comes from molecular fossils, specifically compounds called steranes. Steranes are the breakdown products of sterols, a type of lipid molecule that certain organisms produce. Different groups of organisms make distinctive sterols, and when those sterols are preserved in sedimentary rocks and analyzed, they can tell us what kinds of organisms were present, even when we don't have body fossils. In rocks from the South Oman Salt Basin, steranes appear that match the chemical signature of demosponges, a group of simple animals. The timing is crucial. These biomarkers show up no later than the Clement interlude between the two glaciations. Sponges are among the most primitive animals, lacking organs, muscles, or nervous systems. They're essentially colonies of cells that work together, filtering water through their bodies to capture food particles. But even this simple level of multicellular organization represents a profound leap in biological complexity. Individual cells had to evolve mechanisms for communicating with each other, for specializing into different types, for coordinating their activities toward common functions.
The appearance of sponges during the interglacial period suggests that the first snowball Earth, rather than preventing the evolution of multicellularity, somehow set the stage for it. Two main hypotheses have been proposed for why snowball Earth might have promoted rather than hindered the evolution of complex life. One idea focuses on the isolation of ecosystems. When ice covered much of the ocean, different refugia would have been separated from one another. Gene flow between populations would have been severely restricted. In evolutionary biology, this kind of geographic isolation is known to accelerate the pace of evolution. Small, isolated populations can evolve rapidly because genetic changes can spread through the entire population quickly. Different populations adapt to their local conditions, diverging from one another. When conditions change and the populations can mix again, you have multiple distinct lineages that might not have existed without the period of isolation. The second hypothesis suggests that the extreme stress of snowball Earth selected for organisms with greater cellular cooperation. In normal times, single-celled organisms that reproduce rapidly and selfishly might have advantages. But under extreme environmental stress, there might be benefits to cooperation. Cells that work together might better regulate their internal chemistry, maintain stable conditions despite external chaos, or more efficiently use scarce resources. The cells that eventually formed the first true multicellular organisms were ones that had evolved altruistic behaviors, sacrificing individual reproduction for the good of the collective. Extreme environmental stress might have created conditions where such altruism was favored. When the Morenoan glaciation finally ended, the planet entered another phase of rapid environmental change. The deglaciation brought intense chemical weathering as carbon dioxide levels reached roughly 100 times present atmospheric levels. The extreme weathering also drove major changes in ocean chemistry, including a dramatic acidification-deacidification cycle recorded in boron isotopes. The intense weathering created an unprecedented nutrient pulse, particularly of phosphorus, fertilizing the oceans and enabling biological productivity at levels previously impossible. Throughout the snowball period, the ocean had been stratified, with hypersaline brines at depth and less salty water above, all of it beneath ice. When deglaciation occurred, the heating was not uniform. Surface waters warmed rapidly, while deep waters remained cold, creating strong stratification. Eventually, though, ocean circulation reorganized. Upwelling brought deep, nutrient-rich water to the surface, where photosynthetic organisms could access both the nutrients and the sunlight. The combination of high nutrient availability and abundant oxygen created ideal conditions for life to diversify. Photosynthetic organisms bloomed. Oxygen concentrations in the ocean increased. This rise in oxygen had cascading effects. Larger, more complex organisms require more energy to build and maintain their bodies. They also need more oxygen to power their metabolism. The increase in atmospheric and oceanic oxygen during the Neoproterozoic removed a constraint that had previously limited the evolution of large, complex organisms. Roughly 15 million years after the Morenoan deglaciation, around 600 million years ago, the first diverse assemblage of large, complex organisms appears in the fossil record. These are the Ediacaran fauna, named after the Ediacara Hills in South Australia where they were first discovered. The Ediacaran organisms are strange by modern standards. Many have body plans unlike anything alive today. Some look like quilted mattresses or fractal fronds. Others resemble pancakes with radial symmetry. Paleontologists debate whether these were early animals, a separate experiment in multicellular life that later went extinct, or a mix of both. What's clear is that the Ediacaran represents a dramatic increase in the size, complexity, and diversity of life. Organisms measuring centimeters to meters in length appear. Some show evidence of mobility, leaving trails and burrows in the seafloor. Others were clearly sessile, attached to the bottom like plants. The ecological niches that would later be filled by various animal groups were beginning to be explored by these pioneering complex organisms. Then came the Cambrian explosion, beginning around 541 million years ago. Over a period of perhaps 20 to 30 million years, all the major animal body plans appeared. Arthropods, mollusks, worms, echinoderms, chordates, and numerous other groups show up in the fossil record with remarkable suddenness. These animals had hard parts like shells and exoskeletons that fossilized readily, making their appearance seem even more abrupt than it may have actually been. They had complex organs, nervous systems, eyes, muscles, and digestive systems. They were predators and prey, filter feeders and scavengers. The ocean transformed from a microbial soup into an ecosystem that would be recognizable to modern ecologists. The phylogenetic analysis of modern animals provides another line of evidence connecting Snowball Earth to the Cambrian explosion. By comparing the DNA sequences of living organisms and using molecular clock techniques that estimate divergence times based on mutation rates, scientists can determine when different groups split from one another. These molecular studies consistently suggest that the major animal lineages began diverging during the Ediacaran period, in the aftermath of the Morenoan glaciation. The family tree of animals, when traced backwards, points to an origin in the window of time immediately following Snowball Earth. The genetic toolkit that animals use to build their bodies also tells a story. Genes that control development, determining where heads form and where limbs grow, are remarkably similar across vastly different animals. A fruit fly and a human share many of the same developmental control genes, despite our lineages having diverged hundreds of millions of years ago. These shared genes suggest that the basic mechanisms of animal development evolved early and then were modified and elaborated in different lineages. The origin of this genetic toolkit appears to coincide with the Ediacaran period.
What made Snowball Earth such a potent driver of evolutionary innovation? Several factors likely worked together. The extreme environmental stress winnowed populations, eliminating less adaptable lineages and favoring those with greater physiological flexibility. The isolation of populations in refugia promoted divergence and speciation. The rapid environmental changes during deglaciation created new ecological opportunities. The nutrient delivery and oxygenation of the ocean removed previous constraints on body size and complexity. The repeated cycles of glaciation and deglaciation, with a brief interlude between them, provided multiple rounds of selection and innovation. There's also the possibility that the Snowball Earth glaciations reset the playing field in a way that allowed new innovations to succeed. Before the glaciations, ecosystems were presumably occupied by organisms well adapted to those stable conditions. Breaking in with a new body plan or lifestyle would be difficult when all the niches are already filled. But the glaciations disrupted those ecosystems. Populations crashed, distributions shrank. When conditions improved, there was suddenly room for innovation. New ways of making a living became possible because the old ways had been disrupted. The evolutionary legacy of Snowball Earth is perceptible not just in fossils, but in living organisms. Every animal alive today, from sponges to insects to fish to mammals, descends from organisms that survived the cryogenian glaciations. The genetic innovations that first appeared in that crucible are still present in our DNA. The basic mechanisms of cell communication that allow our cells to work together as a coherent body were refined during the environmental crucible of Snowball Earth. The developmental programs that build our bodies from a single fertilized egg trace back to the Ediacaran innovations that followed the final deglaciation. It's a profound and humbling realization. We exist because life found a way to endure conditions so extreme they seemed incompatible with habitability. The frozen planet that should have been a death sentence instead became a crucible for innovation. The organisms that survived didn't just endure, they adapted, evolved, and ultimately gave rise to the explosion of complex life that followed. The connection between Snowball Earth and the Cambrian explosion isn't just temporal coincidence, it's a causal relationship where the extreme stress of global glaciation set the stage for the greatest diversification of life in Earth's history. The ice that nearly extinguished life instead prepared the way for complexity, consciousness, and eventually creatures capable of looking back across hundreds of millions of years to understand what happened and why it matters. Snowball Earth stands as one of the most dramatic climate events in our planet's history. From the mechanisms that plunged Earth into a frozen state, to the frigid hypersaline oceans beneath the ice,
To the volcanic escape that swung the planet into an extreme greenhouse, these glaciations reshaped not just the physical world, but the trajectory of life itself. What seemed like a catastrophe proved to be a catalyst. The environmental crucible of Snowball Earth didn't extinguish life, it transformed it, setting the stage for the explosion of complex organisms that would ultimately give rise to all animals living today, including us. This story reminds us that planetary systems are far more dynamic than we might imagine, capable of dramatic transformations that operate at the very edge of habitability, yet somehow preserve the spark of life. Thank you for listening.